A very warm welcome to all my friends and students. A very good morning, good afternoon, good evening to all of you. And this is the DADM 3, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series. And this total course duration is 12 weeks, which is 30 contact hours, which when considered into the number of lectures is 16 number, because each one of the lectures are half an hour. And as you can see from the slide, this is lecture number 55, which is the last lecture in the 11th week, and each week we have 5 lectures of half an hour each, and after each week you have an assignment. So, with this ending of this lecture you will take the 11th assignment, and then in the 12th you will finish the course 12th assignment, and then you will have a basically a final examination based on all the concepts which have been covered. Now, if you remember in the last lecture, which is the 54th lecture, it was I only drew diagrams in order to make you understand. So, both for the case when you had the normal distribution to be true and variance for both are equal. Then in the second case, the normal distribution to be true for both the cases. I am only able to draw 2 dimension. In the higher dimension, if I was able to draw, I would have basically shown it. Consider the sphere would be fine, but consider the variance are different for all the 3 normal distribution. It will be a little bit difficult to draw it until unless if I have drawn it earlier, it would take time. So, I just skipped it. In the second case, let me come back to the work or the discussion which was done the last lecture, which is the 54th one. We had considered both normal distribution and variance of x1 was more than x2. In the third case, both were normal, then the variance of x2 was more than x1, and later on, which we will now discuss further on, is basically where we consider both are non-normal, the variance would definitely be different, and how we can basically think about the solution techniques and how they look like, and obviously the solution techniques would be the same, how we can solve it. So, okay, I should basically copy it in the later part. So, it will make sense for all of us to consider. So, this is the first case, both being variance being equal, and alpha 1, alpha 2, alpha 3 are the consecutive values of reliability. In the second case, alpha 1, alpha 2, alpha 3 are the levels of reliability, where the variances are different, for x 1 is more than x 2. In the third case, again alpha 1, alpha 2, alpha 3 are the levels of reliability, and obviously in all the 3 diagrams the solutions are given by the centroid or the center of gravity of these figures. In the circle it is the center. Similarly, for the ellipse is also easy to find, because it will be the midpoint on the major and axis and the midpoint on the minor axis. And these levels of reliability will dictate the solutions which are given by S by the suffix corresponding to the level of reliability. In this case, the variance of x 2 is more than x 1, and remember these are orthogonal. In case even if they are not orthogonal, the concept considering that if the normal distribution would not matter much, it is not difficult to visualize. In the fourth case, we have the distributions are normal, and when we find out the center of gravity, which is given here as this one. So, I should be marking with the blue color. So, this is for alpha 1. So, this is basically S alpha 1, this is alpha S alpha 2, this is alpha 3. So, if I consider this is of reliability alpha 1, this is of reliability alpha 2, and this is of reliability alpha 3. Now, here the concepts of infeasible region or the feasible region are exactly the same as we have been trying to draw. So, this is the deterministic optimum solution is the corner point, and they have the loci of the reliable solution as alpha change is also given. Now, how the overall problem formulation has been done, which I have already considered, but I will go into more details here. So, consider the deterministic problem is given, you have a decision set variable which is x and d. X is the decision variables which would initially be considered deterministic, they can change also, they can be probabilistic also, and d is the set of decision variables. They are not the parameters, we are considering a set of decision variables which is d. So, they can be considered as parameters also depending on the problem formulation. Subject to conditions are like this. You have m number of constraints which I have already discussed g suffix j's, and they are deterministic in nature. So, they are greater than 0. So, they can be less than 0 also, they can be greater than bj's, b suffix j's also. And these concepts which you have for the x is basically bounded between x lower and x maximum, xl and xu, similarly for the deterministic variable dl and du. So, like x min and x max, whatever between which you have that value. So, in case if x values are between 10 to 20 both inclusive continuous, so x min will be 10, x max will be 20. Now, consider it is a minimization problem or a maximization problem, whichever you try to formulate. So, your decision variables would also be x and d, but here x is now probabilistic, and this concept of probability would be brought into the picture through the constraints such that you have a probability of gj's x dp being greater than 0, and that is given by alpha suffix j. So, if there are, say for example, capital J number of constraints, each would have basically a probability of alpha 1 to alpha k, and this alpha 1 to alpha j, and this values of alpha 1 to alpha j's would be the corresponding levels of reliability which the decision maker has for each and every constraint. So, we will basically try to take the collective reliability based on which we find out the best optimum solutions. And subject to constraints are also the same, x is less is between x min and x max. Similarly, for d it is between d min and d max or dl and du. L is the lower limit, du is the upper limit. Now, reliability based optimization can be solved using different methods. One is the simulation method. One is the I will basically go into the decouple method, double loop and single loop methods are there. I will first consider, and other method is the simulation one. So, I will basically talk something about the simulation method, then go in details about the decoupled method. So, consider the simulation method are like this. So, say for example, in the case of the normal distribution, what you had? You found out probability of x capital X is greater than x. I am not going to write because I have been writing this equation time and again. So, let me explain. Probability of capital X, whether in the univariate case or the multivariate case, the concept remains same. Probability of x is greater than small x is, say for example, greater than alpha, and you know the expected value of x, you know the variance of x. So, it will be probability of x minus expected value of x, the whole thing divided by the variance, which now becomes capital Z, and that is greater than equal to x, which now is x minus expected value of capital X. So, small x is basically the realized value which will be realized later on depending on how the simulation is being done, divided by variance of x. So, you will basically have probability of capital Z greater than equal to small z, that is equal to alpha. So, you choose a value of alpha, find out this capital Z, small z, and you choose a value of small z, you find out the value of alpha. So, in this case normal distribution is there in either in the multivariate or the univariate case, life is done. But what happens if they are non-normal? So, what you do is that you want to find out that how many times the distribution random variable x is greater than equal to small x, which has been given, and that is the value of is probability is given. So, what you do is the simulate 1000 values, and considering that you are only simulating one at a time, not taking the sample statistic or the sample estimate. You simulate one at a time, rank them from the lowest to the highest or the highest to the lowest, whatever it is. Now, what is alpha? Alpha is basically the area on the right hand side as per the diagrams which you have been seeing. So, you want to basically consider 1 minus alpha, 1 minus alpha consider is 95%. So, you will keep adding. So, for each of those random variables generated from the minimum to the maximum, there is a corresponding value of probability also. So, x, and consider they are nomenclatured as x1, x2 till x100, consider you have generated 100 values. So, for each of these x's you have the probability also. So, probability of capital X is equal to x1, probability of capital X is equal to x2, so on and so forth is given. You keep adding the probabilities one at a time and find out the cumulative probability. The cumulative value where it becomes exactly equal to 1 minus alpha or some value near that 1 minus alpha, which is 95%, that value of x star is reported. So, you keep repeating, do it 100 times, 200 times, and each time you will have different values of x star. You will try to basically, so if you have done it once, considering that you have the whole population, then you would have found out the best value of x, and that you would have reported and basically completed your optimization problem. So, you want to basically find out at that case where the distribution would be true for that value of alpha, and that considering those values you will basically solve your problem to find out the reliable solution. But in the case you do not have a whole set of population values, you take a sample, generate it, say for example 100 number of times with each set of samples having another 100, and find out x star in each case, and you will basically, depending on what type of distribution it is, if it is an exponential distribution, normal distribution, then considering is extreme value distribution, you will basically take the mean value or the the minimum of that value or the maximum of the value, and then basically report it as the best x based on which you will do the simulation. Now, if you remember, I am not changing the topic, I am coming back to one concept which you have done a long time back, considering the whole course in the first 2 weeks or 3 weeks in the course. We have done something to do with the sensitivity analysis, and if you remember in sensitivity analysis what we did, we basically changed the right hand side by 1 unit, decreased or increased, or basically change the parameters of this the decision variables by 1 unit. So, that will give that if the cost or the profit of x1, x2, x3 basically changes by 1 unit, how does your optimum value solution change? Which means that in the case if it was you are trying to change the right hand side, which is the b value, by 1 unit, it will mean that overall constraint is shifting by 1 unit parallelly. Now, what happens in the case when your distribution is normal, that concept also needs to be understood. So, I will try to basically draw that. Again I am saying these diagrams will be coming up again in the later part. So, hence things would become much clear. So, I will repeat it, please bear with me. So, but these things would be definitely be clear. So, first let me draw the diagram and come here. I will take wait 4 different blank slides to draw it. The diagrams would be almost the same, but I will now highlight at other particular point. So, this is the deterministic solution. Feasible region would be somewhere inside. I will just write it. If required, I will basically mark it, but for the time being, I will just mark it. So, this is G1, this is G2. Now, what is important is that for the perturbations or the sensitivity analysis what we do is that constraint shifts. So, consider the constraints shifting is both are normal and both have the same variance, the first diagram. So, it will be with, say for example, perturbations are happening with 90% reliability, which means if I take the consider this is the normal distribution which you have. Very interestingly, the mean value would be the bold line, and this area which you have and also outside region, because this will be infeasible region, that will give you the level of confidence, the overall breadth. So, it is like this, if I draw it, this line is this line, and the overall region if I am talking about, so this what I was talking about. In the similar way, variance was there and consider the variances are same. So, this is the region. So, again if I, so this diagram actually is if I am permitted, so this is similarly if I draw it here, I will use I should be using a different color. So, it is easy for us to highlight. This is how it is coming. So, these values are, this value is this one, this mean value, the line. So, I utilize this concept. So, these are the level of confidence. So, if you are talking about the level of confidence once the circle is drawn, so that will highlight the level of confidence which I am trying to highlight here. In the case so this diagram did I draw? Yes, I have drawn x1 x2. So, x1 x2 is given. Now, this is normal, but one of those variances are high. So, let us draw it. This is much higher variance. Okay, you should be using the other line, sorry. And in this case, the normal distribution let me highlight the feasible region, it look nice. So, only I am trying to basically mark it because you know which is the actual constraint. And when I draw it, the diagrams would be like this. So, this is the level of probability. So, remember this level of reliability is changing depending on the level of confidence which the decision maker wants to make in the problem formulation. This is much flatter. So, it is spread out. You have the feasible region in the case when the variances are different. In the case x1, x2, 1, 2, second boundary, G1, G2, feasible. I am just repeating the diagram, but trying to highlight. This is the so consider this distribution. In the other diagram, it should have been dotted the boundaries, but I didn't do that. And this is much more spread over. Well, this one much more narrow, dispersion is low. So, I will highlight level of reliability here. depending on the level of reliability which is there. And for this case, so I will draw the diagram. This is much steeper. This is much flatter. This one is the values, and I will highlight the bounded regions. This is the probabilities are given and you can find it out. But similarly for the non-normal distribution, it will get complicated, but you can find it out. So, let me draw it again also for the non-normal case. These two classes are going a little bit slow, but considering that these concepts are important, I thought I will go quite slowly. I will have G1 here, G2 here, this is G1, this is G2, this is the solution in one case. So, it will be like this. Now, the variance would be important, but more important is the distribution per se. I will use the it is possible like this, nobody stops us. So, in this region there is the area. This is the area here. If I consider one case is like this, so the highlighted areas where you want to find out highlighted areas when you want to find out the level of reliability. So, with this I will close the 55th lecture, which is the end of the 11th week, and consider more of once this concept is clear. In the higher dimension, obviously all the things will be repeated. So, we will consider the solution methodologies from the SORI and the most probable point techniques. Have a nice day and thank you very much.